Hi again, everyone. This is going to be a lesson about inner products, length, and orthogonality. So we've got a few topics covered in this one. This is going to be a little bit different from the previous topic we were talking about. And, this is actually something that you might see in a Calculus 3 class. Calculus 3 talks about inner products and vectors and things like that. But we're going to look at this from a linear algebra perspective. So let's go ahead and get started and see what we can do. All right, so inner products, length, and orthogonality. These are three topics that are all related to each other, and we're going to talk about them in this order. Let's go ahead and just get started with the first one. So, definition. Suppose u and v are vectors in Rn. Whenever we say this, of course, we're assuming that n is a positive integer. The important thing is that they're both vectors of the same size. The inner product of u and v, denoted u dot v, is defined as u dot v is equal to u transpose times v. All right, that is our first definition, but I have some things to talk about it, and we're also going to look at some examples. All right, so right away, remarks. First thing I want to say is that this is also known as the dot product. All right, so I might use both of those terms. We might refer to this as the dot product of u and v. So if we're given a vector u, and it's in Rn, and let's stay pretty general here. Let's say the entries of it are u1, u2, all the way up to un, and v is v1, v2, up to vn. Let me start by just pointing out that, we've talked about products in this class, and there's two types of products that I guess we've talked about. There's the scalar product, like scalar multiplication is when you just have a real number times a matrix. A vector does count as a matrix, right? This is just an n by 1 matrix. So we could do scalar products of a vector. The other type of product we've talked about in this class is matrix multiplication. And we can't do u times v. Like the vector u times the vector v, that matrix multiplication would not be defined because this would be n by 1, this would be n by 1, so the dimensions don't match up in the way that we need them to for matrix multiplication. So we can't do u times v. However, we can do u transpose times v, because then everything works out. So watch this. We have u dot v, the inner product of u times v, is, well, we do u transpose. And when you do u transpose, remember, transpose is where every column becomes a row, every row becomes a column. So it's like we rotated the matrix 90 degrees, and we get this times this. Now, is this defined? Does this work out as, the right sizes for matrix multiplication? Well, let's look at the sizes of these. As a matrix, this is a 1 by n matrix. And as a matrix, this is an n by 1 matrix. Okay, so one of them has one row, the other has one column. And look at that, the sizes do match up. Because remember, for matrix multiplication, we need this number and this number to be equal to each other. And they are. They're both n, whatever positive integer n is. Now, when we multiply these, what is the result going to be? What's the size of the matrix going to be? Remember, from matrix multiplication, these other two numbers tell you the dimensions of the result. So it's telling me that when I do this times this, I'm going to get a 1 by 1 matrix. A 1 by 1 matrix is something we don't really talk about much in this class. 1 by 1 matrix just contains one real number. All right, so let's do this matrix multiplication, right? U1, V1 plus U2, V2, and so on. U1, V1 plus U2, V2 plus ... all the way up to UN, Vn. Now, I'll say that technically, this should be a 1 by 1 matrix. But the standard convention is to view this. We write this and we view this just as a number without the matrix brackets around it. All right, so the inner product of u times v, it winds up equaling some real number. This just adds up to some real number. So let's do a little example. And we'll see, like, what is this number used for? Does this tell us anything? Well, we'll see. All right, example, let's say we're given this vector 1, 2, 3, and v is the vector -2, 3, -4. And I'm going to have two parts to this question. I think I'll do part of it, and then I'll ask you to do part of it. First, we're going to compute the inner product of u and v. And then we're going to compute the inner product of v dot u. All right, because we'll see. We don't know if they're going to be the same or not, right? I mean, let's investigate this by doing an example. So I'll get this one started for us. I think I'll do part A, and then I'll ask you to try part B. But there it is in case you're writing it down. All right, so solutions to part A. So u dot v, we take u and do the transpose of it. So 1, 2, 3, and then v just stays the same, -2, 3, 4, -4. And when we perform this matrix multiplication, we're going to get 1 times -2 plus 2 times 3 plus 3 times -4. I guess I didn't have to write so many parentheses, but I did. So we got -2 plus 6 minus 12. So you see you just get a number out of this. And the number I get is -8. All right, so it's not so bad. I'd like you to try part B. So I'd like you to pause the video and try part B here. All right, v dot u is going to be v transpose looks like this. And then the matrix u was 1, 2, 3. I just called it a matrix. I mean, like we said, a vector is a matrix. It's just a thin matrix. We get, let's see, -2 times 1 plus 3 times 2 plus -4 times 3. This is going to be -2 plus 6 minus 12. And that equals negative 8. So we did get the same result for part A and part B. So it looks like when we do the inner product, u dot v or v dot u, it looks like they're equal to each other, right? And we have a name for that kind of property in math. It looks like the inner product is commutative, or the inner product has the commutative property. Now, do you think that that's always true? Is it something special about these vectors I chose, or do you think that's always true? Well, let's look at why did we get negative 8 for both of them. It's because for part A, we were doing, 1 times negative 2. And for part B, we were doing negative 2 times 1. So either way, we got the same result. Like we had negative 2, 6, negative 12, negative 2, 6, negative 12. It's because the effect of swapping around u and v just swapped around these numbers. But we know that when you multiply two real numbers, that kind of multiplication is commutative. 2 times 3 is the same as 3 times 2. So yeah, it does seem like these were guaranteed to get us the same result. So we have a theorem that's going to formalize this. Let's move the page up. So we could say as a property of inner products that u dot v equals v dot u, but this theorem is actually going to have a few properties. That's just one of them. All right, theorem 1 for this topic. Let u, v, and w be vectors in Rn, and let C be a scalar. Then we're going to have 4 properties, and the first property is the one that we were just talking about. U dot v is equal to v dot u. We're saying this in general now, not just for that example. Part B says parentheses u plus v dot w is equal to u dot w plus v dot w. So this looks kind of like a distributive property, right? It's like we're saying that you can distribute the dot product across the parentheses in this way. Property C is going to have the scalar involved, and it says that if you have a scalar times u, and then you do dot v, so, you do what's in parentheses first, so you scale u, and then you do dot v, that is the same as doing C times u dot v. So you can either multiply by the scalar first, or you can multiply by the scalar afterwards. And that's also equal to u dot cv. So the scalar can actually appear in any of these 3 places, and it still gets us the same result. Oh, I said there were 4 properties, so there's one more. This one is going to say that if we do u dot u, the inner product of u with itself, the result is always going to be greater than or equal to 0. There's actually something else I'm going to write on this line, so there's a little something extra. But can you see why this is true? Can you imagine if you took a vector and did the dot product with itself? Like maybe the vector 1, 2, 3. You would have 1 times 1, you'd have 2 times 2, 3 times 3. So even if some of the entries of u are negative, if like some of the entries are negative, some of them are positive, some of them are 0, you're still going to get something non-negative for each one of these, and it's going to add up to something non-negative. You can test that out with a small example if you want. And we're going to say that the inner product equals 0 if and only if u is the 0 vector. That kind of goes along with what I just said. Like, each of these products of real numbers is going to be greater than or equal to 0. So the only way that they're all going to add up to 0 is if they were all, if it was 0 plus 0 plus 0 plus 0. That's how you would get it. So it would have to only happen when it's the 0 vector. All right, so that theorem has some properties of the inner product. Now, we're still going to talk about the inner product in this lesson, but we have other things to talk about also. This lesson was called inner products, length, and orthogonality. So we want to get into talking about length. And we have a definition here. The length, or norm, okay, we'll sometimes call this the norm, of a vector v, denoted by this symbol, double vertical bars around it, is defined by before I even tell you the answer to this, like before I finish this definition, I could even ask you, like, how do you think length of a vector should be defined? Well, I would say that we sometimes draw a vector as an arrow starting at the origin. I guess I'm thinking of maybe the examples that happen in R2 or maybe R3. But, if we had a vector in R2 and we wanted to kind of draw it on the xy plane, we could have the point x comma y, and we could draw an arrow from the origin to x comma y. And then maybe we want to talk about the length of that arrow. So that's really like the distance from the origin to x comma y. All right, I'll tell you the definition. It's going to turn out to be the square root of v dot v. Look at that. So what does the square root of v dot v look like? Well, it's the square root of v1 times v1, v2, v, but we could just write it as v1 squared plus v2 squared plus dot, 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 all the way up to vn squared. And doesn't this kind of look like it's measuring the distance from the origin to the vector? Or instead of the word origin, you could say it's measuring the distance between the 0 vector and v. So here, let's do an example. Let's do an example in R2, because I was kind of visualizing R2 in my head. So let's just do a quick one here. Let's say we have the vector 3, 4, and we want to find the length or norm of this vector. I'll do this one for us. This is quick. This is a quick one. We're just going to use that above formula. So I'll just give you a chance in case you're writing that down. Isn't it just going to be the square root of 3 squared plus 4 squared? And then we see if we can simplify it. So the square root of 9 plus 16, it's the square root of 25, which equals 5. So I have some remarks to say about this. We answered that question. All right, first of all, some of the stuff that I said out loud, I want to write down so that we have it in our notes. If we view R2 as the xy plane, the norm of V is the distance from the origin. Okay, so you could even use the traditional distance formula from 3, 4 to 0, 0. You would have this. This is exactly what you'd get, and you'd get 5. If we draw the vector V as an arrow in the plane, the length of V, or the norm of V, is its length. And I mean, we defined it as length, but I mean, it's the length in the traditional sense. When you talk about the length of a line segment. So let's draw a quick picture of the example that we just did. So I'll see if I can kind of leave it on the screen. I guess this would be in quadrant 1 because both of the coordinates are positive. So xy plane, but I only really need to focus on quadrant 1. X-axis, y-axis. So the vector 3, 4 from the above example. Oh, I need to go higher up here. Let's see. Let's say this is 4 up here. So 3, 4, you could think of it as x, y. It points to about here. Okay, because there's 3, there's 4. Draw it as an arrow, like that. And we're saying that this has a length of 5. So let's move this up. Now, the same thing also applies not just to R2, but to R3 and above. But, you know, it gets a little bit harder to try to visualize it in those cases. So we don't necessarily have to draw it every time. Let me also say, this is still included under my remarks about the definition of length. If V has a length of 1, then V is called a unit vector. So it's a vector with a length of 1. I mean, the one that we drew above had a length of 5, so it's not a unit vector. Given any non-zero vector V, we can divide by its length to find a unit vector that points in the same direction. This is called normalizing V. So we take a vector, we're going to divide by its length. It's going to give us a unit vector that points in the same direction. Now, actually, there's one thing in this sentence that, well, it's 2 sentences, I guess, but there's one thing in this that might stand out to you, or you might want to question is Divide. Can we divide a vector by something? We've never really done that. I mean, we've talked about multiplying a vector by a real number. That's called scalar multiplication. But can we divide a vector by a number? Well, I'll show you an example. Let's continue with that same example from above. So the same vector from above, I mean. So the vector 3, 4, and we found the length to be 5. So let's normalize this vector. Let's find a unit vector, so it has a length of 1, a unit vector that points in the same direction. So if we draw it, I mean, I could even visualize it on this picture. I want a vector pointing in the same direction, but with a length of 1. What would that vector be? So I guess what I wrote above suggested that we take a vector and divide it by its length. That might look a little weird because we're not used to dividing a vector by a number. So how do we divide a vector by a number? It's really quite simple. We just multiply by the reciprocal, you know? So you want to divide by the length of v, just multiply by 1 over the length of v. And now it's just scalar multiplication. It's a real number times a vector. So that's how we divide. Just multiply by the reciprocal. So 1 over 5. Scalar multiplication, 1/5 times this vector. It's going to give us 3/5 and 4/5. And this result is a unit vector that points in the same direction as v, the original vector we started with. All right, so the actual computation was pretty simple. And you could verify if you want that this has a length of 1. We don't have to do that, but yeah, you could do the definition of length, use the little formula, and check out what is the length of this, and you'd find that it has a length of 1. And if you were to draw this vector in the xy plane, you would see that it goes along this same ray. It kind of points in the same direction, but it only goes a distance of 1 from the origin. So I have a problem that I'd like you to try. It's going to be bigger than just R2. I'm going to give you a larger vector. U equals 5, 0, 1, 3, 1. And I'm going to say find a unit vector, v, in the same direction as u. So go ahead and pause the video and try this out. Okay, so the problem didn't tell us this, but I think in order to answer this, we're first going to need to know what is the length of u. So let's go ahead and find the length of u. It's going to be whatever this number is. Square root of 25 plus 1 plus 9 plus 1. 25 plus 1 plus 9 plus 1. Hey, that's the square root of 36. This is going to work out nicely. The length of this vector is 6. So the vector v that we're looking for, notice the problem called the original vector u, and it wanted the answer to be called v. So v is going to be the original vector times 1 over 6. So original vector times 1 over 6 is going to get us 5 over 6, 0, 1 over 6, 3 over 6. Let's not write 3 over 6. Let's write 1 over 2 and 1 over 6. So that's the answer. It is a unit vector, and it points in the same direction as u. Let me just zoom in on that just in case you can't see it. So we normalized u. That's what normalizing means. Now, I think that in our discussion of length over the past few minutes, I think I've used the word distance a few times. I think I've said it's the distance from the origin. And we have a definition for this as well. I guess I was talking about distance in the traditional sense that you've seen before. You've seen it's basically Euclidean distance, and we have, the distance formula from algebra classes. But let's be more precise about this in the linear algebra sense. So we're going to have a definition for distance between two vectors. Given a vector u and a vector v in Rn, the distance between u and v, denoted dist u comma v, is defined as the distance between u and v is equal to, we have a simple formula for this. I guess whatever we come up with, we want it to sort of match with our conventional concept of distance. But we can also use the norm, right? So it turns out you just do the norm of u minus v. And what we mean is this is the length of the vector u minus v. So you take one vector, subtract the other one, and then you find the length. So it's really not bad. I will say underneath this, in R2 and R3, this is equivalent to our usual concept of distance. Between 2 points. Now, yeah, I'll give you a chance just to see that. Now, everything we're talking about when we say length and distance, we're really talking about distance in the Euclidean sense. If you take a class in modern geometry, you might learn about other types of distances and other types of norms. But everything we're doing here is kind of Euclidean geometry. And yeah, there is kind of this nice connection between like algebra, linear algebra, geometry, and calculus 3. So hopefully you see some connections between your different math courses. They're not just isolated islands. They're actually all part of the same big picture. Let's do an example problem. So we just had a new definition, so let's do an example with it. Given the vector u equals 4, -2, 3, and the vector v equals 1, 0, 5, let's find the distance I'd like you to try this one, I think. I don't know. Yeah, try it out. Go ahead, pause the video, and see what you can get for this. Okay, so solution for this. We're expecting the answer to just be a number. We do the formula above. Distance of u comma v is going to be the norm of u minus v. So let's figure out what u minus v is. This vector minus this vector. Remember, we talked about how to add two matrices or how to subtract two matrices. It was a long time ago, but all you do here is subtract the corresponding entries. 4 minus 1 is 3, negative 2 minus 0 is negative 2, 3 minus 5 is negative 2. So to answer this question, we want to find the length of this vector. So the norm of this vector, or the length of this vector, is square root of 3 squared plus negative 2 squared plus negative 2 squared. And the square, oops, I put a parentheses in the wrong place. And the square root needs to go over this whole thing. Okay, so that looks good. So you should have gotten that this equals the square root of 9 plus 4 plus 4, which equals the square root of 17. And that's going to be the answer. So that's the distance between these two vectors. And if we were to draw them as arrows in the three-dimensional space R3, you know, it's a little bit tricky to draw three-dimensional pictures, but if we did, we'd have an arrow from the origin to this point, an arrow from the origin to this point, and this would be the distance between them, between the tips of the arrows. But we can also apply this, you know, strictly speaking, as just a formula and just do the algebra. So this also works for like R4 and R5 and R6. And at that point, we stop trying to visualize it. You know, we don't try to draw a four-dimensional picture or anything like that. At that point, it's more of just a concept of distance that we can still define it. We could still conceptualize it. Maybe we don't visualize it so much. Now, this lesson, what did we have? We said that this is called inner product length and orthogonality. So orthogonality is the big remaining one that we haven't talked about yet. And just like the other two, we're going to start with the definition. Definition, two vectors, u and v, in Rn, so they're both in the same space, so they both have the same number of entries. They are orthogonal to each other if their inner product u dot v is equal to 0. Okay, that is what it means to be orthogonal. I'll show you some quick examples. Example 1. Are the vectors 8, negative 5, and negative 2, negative 3, are they orthogonal? So this is a yes or no question. They either are orthogonal or they're not. And the way that we answer this is we just check, does u dot v equals 0. So that's why it's a yes or no question. U dot v, we know it equals something. We know it, it's going to equal a number. And we said earlier, we said earlier how to do u dot v. Here, 8, -5, that's u transpose. And then v. So 8 times -2 plus -5 times -3, -16 plus 15. -16 plus 15, that's going to equal -1. So it does not equal 0, so we say no, they are not orthogonal. And the work that we showed above justifies our answer. You could even write next to this, when you get -1, you could even say, that's not equal to 0. Let's look at another example. Example 2 are the vectors -4, 2 and 3, 6. Are they orthogonal? I'll show you the steps for this one also. We want to check u dot v, see what we get. So -4, 2 times 3, 6. So -4 times 3 plus 2 times 6 is -12 plus +12. Look at that. It does equal 0. So we're going to say yes. Yes, they are orthogonal. I'm just going to say yes, they are orthogonal. I mean, technically, we could say they are orthogonal to each other. Like, what are they orthogonal to? They are orthogonal to each other. So what does orthogonal mean? I mean, we just had a definition of it. Okay, it's if the inner product equals 0. But what does this represent? I mean, some of the other things we talked about today, we understand what distance represents and we understand what length represents. But what does this actually do for us? So visually, I like to think of this visually or geometrically. Let's draw the vectors from example 2, the ones that were orthogonal, and let's give them a name. Let's call them u and v. And let's see what they look like in relation to each other. And let's figure out if we can see from the picture, can we tell that they are orthogonal? All right, so v goes to 3, 6, so let's make sure that we set this up with a big enough scale. So there's 6. Okay, that should be enough. So first, u we would draw as an arrow from the origin to the point -4, 2. So that would be here. So that's the vector u. And the vector v would be a point from, an arrow from the origin to the point 3, 6. 3, 6 is up here. That's v. So what can you tell about these two vectors now that we drew them? Maybe this gives you a sense of what the word orthogonal is really telling us. Is there something that you notice about these? If I drew it just right, if I drew it perfectly to scale, what's the angle between these two vectors? It's like a 90-degree angle, right? We have a name for that. So key idea, maybe I can write this off to the side. Key idea. Geometrically, vectors orthogonal to each other corresponds to our usual notion of perpendicular lines. Okay? So orthogonal, in a sense, is kind of like saying perpendicular. Now, these are not really lines, right? They're not linear functions. They're not, we didn't draw the whole line. In geometry, you might call something like this a ray. It's kind of like part of a line. But still, just informally, I guess, you could say that being orthogonal is kind of like being perpendicular. Except now we're talking about vectors instead of lines. And also, we're not just limited to examples in R2. We're not just limited to the XY plane. They could be in R3, R4, or a larger space. And we can still talk about whether vectors are orthogonal in R5, even if it's hard for us to visualize what being perpendicular looks like in R5. All right, let me give you an example to try. Oh, by the way, hold on. Before we do an example, let me say a couple of things. We did two examples above where I gave a pair of vectors and I asked, are they orthogonal? And for example 1, the answer was no. For example 2, the answer was yes. Doesn't it feel like if you were to pick two vectors kind of at random, and then you checked to see whether they are orthogonal, it feels like the answer would usually be no. Like it would be a big coincidence if you picked two vectors at random. It would be a big coincidence if they happen to be perpendicular to each other, right? Or thinking about the actual math that we did, it would be a big coincidence if their inner product just so happens to equal 0. So I guess it feels like for a pair of vectors, like most pairs of vectors are not orthogonal to each other. And that's kind of why when you do get a pair of vectors that is orthogonal, it's kind of a special property. It's something that you usually wouldn't expect, and it makes the two vectors, related to each other in this way. And this is one of the uses of the inner product. We defined the inner product at the beginning of this lesson, and we saw that it can be used to calculate length. And now we're seeing that it can also be used to determine whether vectors are orthogonal. So the inner product does a couple of things for us. That's what I wanted to say. All right, so that was my speech. Let me give you an example to try. Given the vector u equals 1, 2, 3, and the vector v equals 2, 0, c. For what values of c are u and v orthogonal to each other? It's a different type of question. All right, so I'd like you to pause, take a minute, and try to answer this. So notice that in the question I said values with a possible s. So let's see what we get. Well, we want to check u dot v. We want to know when this is 0. So I guess this is 1 times 2 plus 2 times 0 plus 3 times c. You can go ahead and just set this equal to 0 and solve for c, right? We want this to equal 0 in order for these things to be orthogonal. So, all right, this simplifies to just 2 plus 3c equals 0. 3c equals -2. So c equals -2/3. And that is the answer. If c is -2/3, then u and v are orthogonal to each other. And that's the only value of c that works here. All right, so that's going to be it for this one. We covered a few different things in this video, and the three big things are in the title. It's the inner product, length, and orthogonality. So orthogonality is just a word to describe this concept of whether or not vectors are orthogonal. And we learned that that is similar to saying whether or not they are perpendicular. So some things just to take away from this lesson. You should know the definition of the inner product. If I gave you two vectors, you should be able to compute the inner product. You should know the definition of the norm of u, also known as the length. You should know how to calculate that. You should know about unit vectors and normalizing vectors. We did an example of that. And distance between u and v. See, there are a lot of little things in this lesson. Each one is not really that hard, but it's a lot of little things to keep track of. The distance between u and v, it was the norm of u minus v. And then the definition of orthogonal and the last couple of things we did. All right, so that's going to be it for this one. This is kind of just an introduction to this topic. There's more that you can do with orthogonality, but this was hopefully a good introduction to this concept. All right, so that's it for now, and take care. I'll see you soon.